Page 5 of practice exam 3. Provide the Fisher projections and names of the linear forms of simple sugars A, B, and C. And we're given the epimer data for the different names of monosaccharides. All right, so I think a good place to start with all of these things is to number the sugar carbons. All right, so this is going to C1, C2, C3, 4, 5, 6. On C, this is going to be anomeric. That's 1, 2, 3, 4, 5, 6. On carbon B, anomeric 1, 2, 3, 4, 5, 6 for carbon A. Alrighty, so for carbon A, so these are all pyranoses, so 6-membered rings. They're all 6 carbon sugars, as obvious by the Fisher projections. All right, so we'll start with sugar A. All right, so the anomeric carbon, okay, this is going to be an aldose. Okay, so actually all of these are going to have an aldehyde at C1. Okay. All right, so remember, in order to form a Haworth projection, we turn the Fisher projection 90 degrees clockwise. All right, so anything that was on the right of the Fisher projection is down on the Haworth. So at C2 on carbon, in sugar A, at C2 the OH is down, so that's going to be on the right. Okay, hydrogen would be on the left. Carbon 3 OH is on the right, because it's down, H on the left. All right, carbon 4 OH on the right, hydrogen on the left. All right, carbon 5. So carbon 5, when you have the CH2OH group up in a Haworth, that means that this is a D sugar. So OH is going to be on the right in that last stereocenter. Okay, and C6, of course, has an OH group on it. All right, carbon B. I'm going to switch colors just in case it's kind of bigger than it needs. Let me zoom in. All right, carbon B. All right, carbon 1 has the aldehyde on it. Again, carbon 2 is the OH is down, so that'll be on the right. Okay, OH is up on carbon 3, so that'll be on the left. Okay, carbon 4, the oxygen is down, that'll be on the right. Carbon 5, again, has the CH2OH group up, so that's going to be on the right. And we fill in our hydrogens. Okay. So for C, oh, I missed the hydrogen here. So for C, again, C1 has that aldehyde. All right, C2 OH is down, it's on the right. Switch colors again. OH is on the right. C3 OH is on the left because it's up. C4 OH is up, so that's going to be on the left. And again, that CH2OH is up on C5, so the OH will be on the right. Okay, we fill in our H's. Don't forget your C6 OH groups. All right. So, by looking at compound B, you should notice that this is glucose. All right. So you should be able to draw that from memory. You should definitely be able to recognize it. That's D-glucose. So if we compare B with A, we see that one stereocenter is switched. So this is a diastereomer. Right? And when a one stereocenter switch has occurred between diastereomers, it's also called an epimer. Okay, so the one stereocenter that has switched is the C3 position. All right, and so we see that allose is the C3 epimer of D-glucose, so this is D-allose. Okay, sugar C, carbon 2 is the same, carbon 3 is the same, carbon 4 is not the same, and carbon 5 is the same. All right, so this is a C4 epimer. All right, galactose is the C4 epimer of D-glucose. So that is galactose. Alrighty. What is the reaction sequence for a wall degradation? You should look that up. You should flashcard that. What is the reaction sequence for Kiliani-Fisher elongation? Also, that's flashcard chemistry. Propose a synthesis of C starting from B. All right, so this is a little bit tough. Okay, so we look at B and we look at C. We want to make C from B. All right, so what we need to do is we need to compare these things. All right, and we'll start from the bottom, right? Because what we're going to have to do, you should be comfortable with the fact, by the time you take the exam, that you're going to degrade monosaccharides from the top down. Okay, so we have to remove the top carbon, and then if we need to remove another one, we remove C2 and then C3. All right, so we're going to start from the bottom to see what we need to fix here, or what we need to adjust. All right, so going from B to C, we do not need to worry about switching the stereocenter at C5. However, the next one up, this is a switch, all right? The C4 is epimerized, okay? So what we need to do is we need to take off this carbon, all right, which would make C2 the aldehyde carbon. All right, but we need to epimerize C4, so we need to take this off, okay, and then take this off, all right, and that would make, when we take that off, that would make this carbon, that C4 carbon, that would make that an aldehyde, okay, and so we don't need to take that off, we need to start hitting that with our Kiliani-Fisher synthesis, and we need to build it back up. So we're going to make a mixture. Okay, you don't have to make pure C, you just have to make C. All right, so we have to take off 3 carbons, which means that we would do 3 wall degradations. And we still want to make a hexose out of this. All right, so we'd have to put 3 carbons back on. Each one would generate a more complex mixture, but we would still make C. So the answer to the synthesis question is you do 3 wall degradations followed by 3 Kiliani-Fisher syntheses, and you've got yourself C. Alrighty. Propose the most efficient synthesis of D-ribose from either A, B, or C. All right, D-ribose, you might recall, well, you should know what D-ribose looks like. All right, it has 3 OH groups, all on the right. All right, so we happen to have 3 OH groups on the right of the bottom of D-allose. All right, so in this case, all we have to do is we have to remove the first carbon of allose. That'll form an aldehyde at C2, which will become C1 of D-ribose. And we're done. So it's just one wall degradation sequence. Remember, that's a 3-step sequence. All right. So for these kinds of questions, you don't have to write all 3 steps, however many times it takes. Just say 3 wall degradations, 3 Kiliani-Fisher, or in this case, just 1 wall degradation, and we're good to go. All right. What glycosidic linkages are part of the trisaccharide shown above? All right, so this is another good reason to number the carbons at the beginning. All right, so remember, glycosidic linkages are anomeric bonds to something other than OH. All right, so let's go with blue. All right, blue. So here we have a glycosidic linkage, all right, and we see this is a C1, all right, bound to a C6, all right. We also know that this OH here is down compared to the C2 OH up there, which is up, all right. So this is trans, so this is going to be an alpha 1 6' glycosidic linkage, okay. On the next carbon, the next sugar, the anomeric carbon doesn't have a glycosidic bond. It just has an anomeric OH group. Okay. However, sugar A does have a glycosidic bond at C1. Okay. This oxygen, this is up. This CH2OH is up. These are cis, so this is beta. Okay. 1 for the anomeric carbon. This is bound to the 4 position of carbon, or sugar B, excuse me. So this is a beta 1,4 prime glycosidic linkage. And that's all there is to that.